Good morning, I'm Dr. Tianchi Zhang. I'm from the College of Mechanical and Electrical Engineering of Nanjing University of Aeronautics and Astronautics. My research topic is toughness-improving design of lattice sandwich structures. First of all, we should know about the lattice sandwich structure has become a focus of research in aerospace and other fields because of its lightweight and high impact resistance. However, research on the impact resistance of lattice sandwich structures is still focused on simulations and experiments and presently lacks theoretical models. In our works, we proposed a toughening design method based on the failure modes of lattice sandwich structures. The toughening model was established, the dimensional effect was analyzed, and the mechanism of synergistic toughening was studied. Advanced lightweight structures have become a focus of research due to the urgent demands for lightweight materials, with high mechanical properties in the fields of aerospace, vehicle engineering, and biomedicine. The porous sandwich structure, as a lightweight structure with room energy absorption ability, has superior impact resistance. Therefore, it has received much attention from researchers. At present, research on the mechanical properties of porous sandwich structures mainly focuses on the mechanical response, failure mode, damage mechanism, and impact resistance under different load conditions. For characterizing their impact properties, scholars have explored the effects of geometric factors on sandwich structures, such as the thicknesses of skins, configurations, and sizes of cores. Studies have shown that the core is the key to improving the impact toughness of sandwich structures. Some researchers noted that, in metal sandwich structures, the impact energy is mainly absorbed by both the core and the top plate, while plastic dissipation is the main form of energy absorption for this structure, and some researchers found that a core with low density shows a better cushioning effect, and when the density increases to a certain degree, the cushioning effect decreases. Three-dimensional lattices have mechanical properties of lightweight, high specific stiffness and strong energy absorption. Therefore, they are excellent configurations for cores. A three-dimensional lattice was first proposed by Professor Gibson and Professor Ashby. In the next 2 decades, scholars carried out research on the mechanical properties of lattice structures driven by engineering applications, such as octet truss, cagone, tetrahedron, pyramid, BCC lattice, the body-centered cubic lattice, and other new lattice structures. Among them, the work on quasi-static loading was mainly focused on the exploration of structures with high modulus, high strength or strong energy absorption. Some researchers imported several deformation modes for rods of the lattice, and they deduced the elastic modulus of the BCC lattice with Timoshenko beam theory. Some researchers demonstrated that the strength of lattice structures can be enhanced effectively by preventing the buckling of struts. Some researchers noted that the property of energy absorption for lattices is mainly reflected in the plateau stress stage. Some researchers established a theoretical model of a sandwich plate with a tetrahedral lattice core under compression and shear loads. Some researchers found that the stiffness and energy absorption capacity of lattices can be improved by a reasonable gradient of relative density. and some researchers proposed that the compressive strength, plateau stress and energy absorption of lattices can be enhanced by a dual-phase structure with an appropriate reinforcement phase. In addition, the key technology of toughness-driven design has also made a breakthrough in recent years. When under a dynamic load, the mechanical behavior of lattice structures will depend on the strain rate. Its deformation mode and failure mechanism will also be changed by the strain rate. Some researchers noted that the strength and energy absorption capacities of lattices improved with increasing strain rate at the stage of low velocity impacts. When the strain rate is further increased, the inertia effect should be added. Over the years, researchers have also carried out much work in the research directions of low-velocity impacts and explosions to explore the mechanical responses of lattice structures under dynamic loads. When studying the low-velocity impact for lattices, some researchers found that the failure mode of lattices can be changed by the gradient structure, and this gradient lattice can enhance the crashworthiness of parts. Some researchers found that the multilayer lattice structure has a higher energy absorption effect when studying the explosion resistance of lattices underwater. Some researchers proved that filling the intracavity of thin wall tubes with lattices can improve the impact energy absorption of tubes in the axial direction. And some researchers evaluated the deformation mode of layered hybrid lattices by the drop hammer method, and the split Hopkinson pressure bar under dynamic loads. Taken together, the existing studies of lattice structures mainly focus on the basic mechanical responses, energy absorption effects, and reinforcement effects of the lattice core on sandwich structures, although scholars have explored the impact energy absorption of lattice sandwich structures to seek high toughness and impact resistant structures. These works mainly involve experiments and simulations and lack theoretical models. The synergy of the core and walls is neglected in these works as well. In our study, we coupled the BCC lattice between the walls of the sandwich structure to form a lattice sandwich structure. The toughening mechanism and design method were studied systematically. To supplement the existing research work in the field of lattice structures, the mechanical characterization of the lattice sandwich structure is described. The finite element simulation method for toughening design is also provided, and the dimensional effect and the mechanism of synergistic toughening is studied. The high mechanical properties of the sandwich structure are derived from the porous core and the thin walls with a high elastic modulus. This structure places the walls in the state of plane stress. The porous core can not only change the whole stiffness of the structure, but also provide more deformation space. Benefiting from these factors, the lattice sandwich structure has high toughness and impact resistance. And the lattice structures can be divided into two types according to the loading mode, compression-dominated and bending-dominated. The former mode has a higher loading capacity, and the latter mode can provide better deformation. Therefore, using bending-dominant lattices as the core can provide better deformation and lightweight. And this is the mechanical constitutive model of the core, which is affected by the bending or the plastic hinges of the rods of lattice structures. And we can also get the failure modes of the sandwich structure by the equivalent stiffness of the whole structure. Then according to the failure modes, some interesting things can be found. The impact toughness of the lattice sandwich structure is affected by the rod radius of the lattice structure. Within a certain domain of the rod radius, the impact energy absorption of the sandwich structure decreases with decreasing rod radius, which means that the impact toughness declines gradually as the rod radius decreases. However, when the radius of the rod is reduced to a certain degree, the dimensional effect will arise. In this state, the impact toughness of the lattice sandwich structure increases significantly, with the synergy of the core and skins. Then, we describe our deduction by simulation and experiment. For simulation, we solved the flow stress in combination with the Johnson-Cook models. The results show that, when using the simulation method, tonally is the impact toughness of the samples. The change trend of the impact toughness is consistent with the actual test results. Therefore, the method of simulation analysis can be selected to drive the design of BCC lattice sandwich structures, and it can also predict or analyze the impact toughness of components. And the experiment results show that, for the BCC lattice sample with thick rods, in the process of fracture, tear-type cracks appeared in the core. The absorption effect of the energy of tear-type cracks is higher than that of open-type cracks. In addition, the lattice structure can ensure enough materials in the direction perpendicular to the crack surface. The plastic zone can extend along the rods of the microstructure. The core rod diameter is relatively thick, such that the impact load can be easily transmitted to the bottom by inclined rods. Then, the crack is caused at the V-notch. It propagates along the direction of maximum shear stress. In addition, the compressive stress in the top skin can inhibit the formation and propagation of cracks, resulting in this area rupturing last. And the lattice structure samples also form discontinuous cracks. Thus, the components continually repeated the process of initiation and propagation of cracks. Because the energy expenditure of crack initiation is higher than that of crack propagation, cores with lattice structures can improve the impact toughness of components. For the core with thick rods, the impact toughness of the microstructure samples decreased with decreasing rod diameter. This is because, according to the fracture criterion, when the stress at the front of the crack decreases with the reduction of rod diameter, the strength factor decreases as well. This causes the fracture toughness of the core to decrease. Similarly, the energy absorption efficiency by deformation of the microstructure core also decreases with decreasing rod diameter. Therefore, the impact toughness of the samples decreases dramatically when the rod diameter decreases. It is interesting that the structure with thin rods has a dimensional effect. With this effect, the core and the skin could synergistically improve toughness. When the rod diameter decreases continuously, the stiffness and bearing capacity of the core are reduced rapidly, and the impact loads are difficult to effectively transfer from the top to the bottom of the sample. As a result, the stress value of the bottom skin is low, and the intensity factor is smaller. Therefore, the fracture toughness of the bottom skin decreased. However, when the top skin is loaded, it produces several plastic hinges, which enhance the energy absorption efficiency. In addition, the expansion of the plastic zone is also conducive to the unloading of stress at the crack tip, and increasing the fracture resistance of the top skin. The deformed skin extrudes the internal space of the structure, resulting in deformation and damage to the core. Then, the impact toughness of the samples is further improved. In summary, in this study, we investigated the design strategy of lattice sandwich structures for systematically improving toughness. A toughened model of the lattice sandwich structure was established. A toughening design method was proposed based on the failure modes of the structure, and the synergies of the core and skin caused by the dimensional effect of the lattice were discussed. As a result, the variation trends of the impact energy calculated by simulation are consistent with the measured results. When the rod diameter decreases, the impact toughness of the structure decreases at first, then increases, and finally decreases. The toughening design strategy proposed in this study can provide a technical method for the design or development of lightweight and high-toughness structures with energy absorption. The lattice sandwich structure we designed is helpful for realizing the lightweight design and improved impact resistance of typical structures found in aircraft. And the contributions of our study are summarized as follows. First, the toughened model of lattice sandwich structures was established based on the characteristics of the lattice structure. Second, the design method of lattice sandwich structures for improving toughness was proposed based on the failure modes of lattice sandwich structures. Third, the failure mode and fracture characteristics of the lattice sandwich structure were analyzed under a low-velocity impact load. Last, it was found that the sandwich structure had a dimensional effect. With this effect, the core and the skin could synergistically improve toughness. Thank you for listening.